A very good morning, good afternoon, good evening, depending on whenever you are seeing this recorded presentation. Myself, Kshitij Rathore from the NISER Bhubaneswar, located in India, working under the well-known personality in the field of Spintronics, Dr. Shubhankar Vedanta. Before starting, I would like to thank Professor Giovanni Pinocchio and his organizing team to accept my application and giving me this golden opportunity to join this fantastic school on the Spintronics fundamental and applications. So me as a research beginner is starting my research as a career, and in the field of spintronics I am beginning with ferrimagnetic spintronics. So I would like to share in the same. So this would be the content of my slides, where I will start with the introductions, literature survey, and then smoothly passing through experimental techniques, results and discussion, and summary and future plans. Spintronic field now doesn't need much of the basic introduction. Due to its high growing demand of the faster, smaller, efficient devices, it's quite interesting that we have come up so long way just after exploring the electron spin as an additional degree of freedom and getting so much of applications perspective as a sensors, data storage, MRAMs, etc. In terms of physics, when I talk about the ferrimagnetic materials, they are very useful as they possess multi-lattice material. So it's an antiparallel lattice material like an antiferromagnet, but this one you can easily measure because of its large magnetic optic effect and large transport effect, where as an antiferromagnets on the other hand can be quite hard to measure because both the sublattices have same nature, and so it's very hard to distinguish between them. As the two sublattices are strongly coupled, then you have to reach out the very high frequencies also. And for the application spintronics, which deals with how to use the magnetic materials to build devices, these materials have interest for the two things: magnetic order with very little ms giving rise to small stray field. That is, if you can say, in devices where you can make them in devices you want to store informations with the magnetic domains. This means you can make them smaller and more tightly packed without fearing for the interaction. And as you can control over the angular momentum density, you can control the magnetic precision. So this means we can build faster switching MRAMs, preventing other effects that comes from the magnetic precisions like the deflection of skyrmions, moving in the domain wall, etc. So to look over this dynamics, we see here about how the magnetization precision occurs, which is given to us by the famous Landau-Lifshitz-Gilbert equation, which we say as LLG. This equation in magnetization is nothing less than the Schrodinger equation in the quantum mechanics. This started with the LL equation, where you can see through the equation that both the terms are on the negative form. So when there is the precision, it goes on forever. But this is not so in the reality. Thus, the equation was modified to the LLG equation, where gamma is nothing but the Landau factor times the Bohr magneton over reduced time scales, and this alpha is nothing just the nothing just a dimension less parameter, and m cross dm by dt is damping like torque. Schematically, you can see this m and h giving this rise to this tangential force. This is a m cross dm by dt, which is allowing to precise this in this cone. Here, without damping, it will precise all this time. But we know the spin are connected to the lattice interaction, and various other fact. So finally, energy will be dissipated. So this damping constant is connected via intrinsic proximity, spin pumping, and impurity, and which overall is found using these two equations when plotted for the ferromagnetic resonance of F versus H resonance, and then delta S versus F. And then fitting parameters are used to count out the energy factors and damping values. So well, as a spin pumping enhances the damping, so finding the right spin pumping voltage is also a major task. This generation and detection technique of spin is spin Hall effect. We know spin accumulation is the SHE cannot be detected quantitatively, and the process of conversion of spin current to the charge current is known as inverse spin Hall effect, where we inject the charge current into the heavy metal. Due to the spin orbit coupling, spin up and down get that accumulated at the different edges and creating opposite sides pure spin current. For this detection of a pure spin current, many years back ISHE was found, which is nothing just the inverse of spin Hall effect, Essentially, we inject a pure spin current to same mechanism, spin up and spin down electrons are scattered towards the same direction, resulting in a charge current. As we can say, in a charge current, spin up and spin down are more or less balanced, but in spin polarized current, number of up and down spins are unequal, to which spintronics is mainly utilized. As less electron will be involved, the less energy consumption will be there. But now let's consider when there are only two spins, up and down, where one moving to the right and other moving to the left, can pass the two spin information, and this is called pure spin current. With no charge current, this will work equal to passing the information from 6 up and 4 down in the same direction. There is another class of this pure spin current which is spin wave and has angular momentum transfer through this spin wave propagation, and this can happen in the magnetic insulators as no involvement of moving electron is there, so no joule heating approximately. Thus, we go with the special class of ferromagnetic insulator. There, as we know, the below TC spins will be aligned anti-parallel without cancelling each other. Thus, we choose the class of rare earth garnet materials, and from that, why will not we choose yttrium and garnet, such a great material having the low damping, and one of the material that we will go in choosing will be TMIG, that's thulium ion garnet, just to explore this physics of it. And as we know, YG is a very complexly bonded out with a dodecahedral structure and the octahedral and the tetrahedral sides having three iron ions, etc. So this is a has a great physics to explore in it. Thus, we go ahead with these thermally and a chemical stable material. Going through this great paper of a controlled enhancement of a spin current emission by 3 magnon splitting, I found that unlike charge current, spin current is not a conserved quantity within the conduction carrier system, which is again due to the spin lattice interaction. Even the axis of angular momentum in the magnetic subsystem flows with that lattice, but this can be reversed by 3 magnon splitting process. Thus, this helps in modifying the spin current emission, and in this YIG magnetization dynamics was studied using the network analysis with the help of microstrip transmission line and use the BLS spectroscopy to access the short wavelength spin waves. In this another classic material TMIG, films were grown on the GZ substrate with a PMA on the top of which heavy metal platinum was fabricated. Interestingly, this 25 nanometer thick film was showing the PMA and exhibiting damping of 0.014 and the Rayleigh factor of 1.556 at 350 Kelvin when attributed in FMR conditions, which is quite close to literature reported values. Well, addition of platinum or copper platinum overlays resulted in enhancement of the damping contribution, which is obviously due to the spin pumping. Also, the low damping, high spin mixing conductance, low electrical conductivity, low corrosivity PMA argues the CMIG as a key material for the spintronic devices. So control of spin current and carried by the magnon in this magnetic insulator is of a great interest to the spintronic field. So the temperature gradient to generate the pure spin current is the key in this generation technique, which we are seeing here as a spin seebeck effect. In the magnetic insulators and non-metal bilayers, where non-metal being normal metal providing it strong spin orbit coupling, the PMA benefits the SOT driven magnetization switching by lowering the needed current and rendering the faster, which is crucial for the developing the SOT MRAMs. So here comes the thin film fabrication part. So as many of the oxide film techniques uses more strongly encouraged, here we have also used our pulse laser deposition technique to fabricate the ferrimagnetic film that I am going to show in the further slides. This technique is mostly preferred due to its control parameters like laser energy, frequency of pulses, temperatures in chamber, substrate to target distance, and oxygen gas pressures, etc. Varying which we got optimized conditions for the YIG and TMIG targets, whose plume is shown here in the picture B. This is the design of our chamber, and after fabricating this insulating layer of magnetic insulator layer from the target, we fabricated the platinum in our sputtering chamber which was located near. Obviously, we had to break the vacuum for this. So this is another absolute state-of-art technique, which is CPW-based FMR, to detect the ferromagnetic resonance, in which we have incorporated the ISC setup to find the spin pumping voltage. Here, these Helmholtz coils maintain the magnetic field outside, and the coplanar waveguides are used for the traveling of coplanar waves, and then that which perturbs the thin films and spins of the samples, which gets split it into down to the energy level due to their plus half and a minus half spins, and when which they come back to their original position after the precision, it gets passed to again to the CPW and then to the diode detector, which passes to the lock-in amplifier, giving this absorption curve, which you are seeing. This is in an absorption spectra, and whose derivative we see as the ferromagnetic FMR derivative, whose this crossing over point is the H resonance point, and this peak to peak distance is delta H, what we say and use for the fitting parameters. And for ISHG, we measure the voltage across the sample simultaneously with FMR spectra using a nanovoltmeter. So now here are the sample that we fabricated on the GGG substrate, YIG platinum, GGG TMIG platinum, GGG YIG TMIG platinum, GGG TMIG YIG platinum, and these were the peaks that we have seen in the XRD of the G substrate. This is a substrate, and this is TMIG YIG when they both were fabricated, and this is a single layer TMIG film. And we compared them with the GGG substrate, obviously, which is not shown over here, and found these different peaks of the YIG and TMIG film. And this is the quality TEM data that we can see that we have done in the NISER setup. As a cross-sectional TEM image, this YIG film is of 85 nanometer, this TMIG of 35 nanometer, this is the CC substrate, and you can see the clearly good epitextual film bone. This is the interface of the TMIG and YIG, which has a smooth interface. These are the FMR data of frequency 2 to 12 gigahertz frequency, where there is spikes represents the resonance point of the samples like YIG with n equal to 1 modes and n equal to 0 modes, which has multi modes in it. And this is all for TMIG, which are having the little bit less prominent peak with this S3 sample with the YIG and TMIG both peaks over there. It's less visible for the TMIG. When we zoom it, we can see the clear image. And for this same for the other bilayer, we use these FMR data to find out the H resonance and delta H, and then further find out the damping values, and finally we are measuring the spin pumping voltage also across them. And now this is the spin pumping values, and this is just a preliminary graph of the spin pumping voltage that we determined for the YIG platinum, and this one is for TMIG YIG. That's as you can see for the S3 sample, and this is the absolutely a TMIG spin pumping value, and this is obviously a YIG which has a higher value. And here, since the TMIG is on the bottom layer, so the planetary platinum will not be able to diffuse to this cross over this YIG thickness, as it's of 85 nanometer. So the TMIG spin pumping value was almost negligible here. These are the fitted values. This is the FMR derivative, and this is the symmetric and anti-symmetric data that we have fitted and find out the spin pumping values for all the data. As you can see, these were fitted using the symmetric and asymmetric equation that I have shown in the earlier magnetization dynamics slides. So these are the quite interesting spin pumping voltages of the different samples. When compared with the S1 and S4, the YIG one on the TMIG has more spin pumping voltage, which was quite interesting to know. But we are yet to analyze more of the TMI, single TMIG and other values to find out the spin mixing conductor and spin Hall angles. And also when we compared the H resonance and delta H of the single layers with the bilayers, there was major shift in those with the bilayers. So I read out for the couplings, so we have to find out those also. So we need to complete the spin pumping calculation and analyze them. We will also focus on the asymmetric switching, Magnon coupling, if present at some low temperature, PNR for the interface study, spin Seebeck for the bilayer samples, and then stabilize the PMF for exploring the spin wave propagation and domain wall motion and spin textures also. So I would like to and then thank Dr. Shubhankar Vedanta for his support and giving me this golden opportunity to work under his group. And I would also like to thank other LLM group members to carry out this work with me. Thank you.